Assalamualaikum warahmatullahi wabarakatuh. My name is Noshira binti Ahmad Safawi. My matrix number is BE30503. We are from Group 4. So today our group will do a presentation about the PID controller design for speed control system. So this is my group member for Group 4, which is me, Noshira binti Ahmad Safawi, Abu Ahya bin Murad, Muhammad Adi bin Omar, and lastly Muhammad Awad. Next, firstly, I will explain about the introduction. DC motor has speed control capability, which means that the speed, torque, and even direction of the rotation can be changed at any time to meet a new condition. The combination of the Pro DC motor has speed control capability, so means that the speed and RS can be changed at any time. So PID controller are the commonly used to regulate the time domain. So behavior of the many different types of dynamic plants. This controller are extremely popular because they can usually provide good closed loop response, characteristic, proportional, integration, and derivative control action is called PID control action. Next, I will continue with literature review. The DC motor has permitted turning difficulties, poor stability, and improper charge control. According to the controllers, the PID controller was designed to make control system more stable, anti-interference, ability stronger, overshoot smaller, response speed faster, and robustness stronger. The structure chart of PID control has been designed and simulated. Fuzzy rule of KP, KI, and KD are also been developed.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adi bin Omar, matric number DE20043. So for today, I'll be explaining about the problem elaboration and the conclusion. So starting off with the problem elaboration, the problem is to design the PID control system for controlling the speed of the blade with a motor DC as an actuator. So in this modern industrial age, there is hardly any industrial application in which DC motors are not being used. Some industrial applications which are worth mentioning in which DC motors are being used widely are machine tools, paper mills, textile industry, electric tractions, and robotics. So the flexibility in controller design of DC motors is due to the fact that armature winding and field winding could be controlled separately. And so this gives excellent speed control performance over a wide range of desired values. There are different types of controller like lead lag, linear quadratic regulator, PID, and sliding mode control that could be incorporated in control applications. And so PID controller is one of the earliest and best understood controllers which is incorporated in almost every industrial control application due to its efficiency and ease of implementation. So for tuning PID controller through these techniques, expertise and experience are required. This is so because these methods provide a starting point and achieving desired performance. Fine-tuning of parameters through hit and trial method is required. However, meta-heuristic techniques may be a good choice to its dynamic nature.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Hamad Abdullah Awad. I'm a master of BE190015. I am Group 4 Control System. Tonight I would like to explain my part of Group Assignment 6.1 Mathematical and Block Diagram Derivation. In this table 6.1 DC motor data show us different value for our parameters. Rate motor terminal voltage we have 24 volt. Moment of inertia of the rotor we have 0.22 kg. Electric resistance we have 11.2 ohm. After that we will proceed in our Laplace transform. First Laplace transform of armature circuit equation 1. Then we'll proceed force equation applied to motor, then Laplace transform of electromechanical equation. After that, from equation 1 and from equation 2 and 3, we will took as a 1. Then we will insert equation 4 and 5 to equation 1. We assume ZA equal bracket GT bracket S square plus PT bracket S bracket R plus LS bracket. Therefore, we will insert the value of this metadata into the equation. We will get 1.28 far by s square bracket 0.44 times 0.121 bracket plus s square bracket 0.44 times 1.2 bracket plus bracket 0.0035 times 0.121 bracket plus s bracket 1.28 times 1.25 bracket plus 0.0035 times 1.2 bracket. Then lastly transform function will get 1.28 divided by 0.0295 s cubic plus 2.7332 s square plus 1.6392 s. Thank you.
Hello, my name is Abu Akhil Abi Murad, matrix number DE200096, and I'm going to present the manual tuning of PID gain. So for the manual tuning, we are going to use the Ziegler-Nichols second method. So after we found the transfer function, now we can use the Ziegler-Nichols second method. We first need to determine the characteristic equation CE, which equal to 1 plus KGS equal to this, we get here. And then we need to use the Roots method. So our largest S is S cube, third order. So just like and then we need to find the AB. For A, we are going to using the cross multiply method. So this times this minus this times this, which we get A equals to 4.4803 minus 0.03776k over 2.7332. And then for B, we're also going to use the cross multiply here. From A, we get A will times this, and then this will times 0. So and down here is A, and we get cancel each other, and we get B equals to 1.28k. And then in order to give equation a stable condition, we take A equals greater than 0, and then we bring 2.7 through 2.7 here. So it will be 4.4803 minus 0.03776k greater than 0. And then negative 0.00377k over ni. And then lastly, we will get k is 118.652. And then second, we take the B, 1.28k greater than 0. So k greater than 0. So for stable condition is 0, lower than k and lower than 118.652. Thus our value of k critical, KCR, is 118.652. And then with the KCR, we can find the imaginary roots. 2.7332s square 1.28k equals to, and then we put the value of k, which is this. And then we have s square equal to negative 55.5666, and the root we have is plus minus j 7.4543. So we get the limiting value. We can find the PCR, which is rate of oscillation, which is 2 pi over the k. And then we have the 0.84 second. And then when we have the KCR and PCR, we can finally manually find the PID gain, the PI and PID gain with this Ziegler-Nichols second method table. So here it say for P, Kp for P is 0.5 KCR, which so we put 0.5 times the KCR here, and then we have 59.326, and then Pi 0.5 KCR, which we get for 53.3934, and then Kp for PID, which is 0.6 KCR, we get 71.1912, and then for Ti of Pi, we get 0.7, Ti for PID 0.42, Ki for Pi 76.2763, and Ki for PID 196.5029, and then Td we have 0.105, and Kd for PID we have 7.4751. Hello, now we are gonna proceed with the simulation of the block diagram in MATLAB Simulink. So it says here B, implement block diagram of the system for input speed and output is black speed, and run the system for input speed 900 rpm and 1500 rpm, and record the response attached on the report. So let's go to the MATLAB Simulink here. So first, to do the block diagram, first we need the subsystem or the transfer function. So we're going to do the subsystem first. So this is the subsystem for this transfer function. So we're gonna put this on the report. And after we're done with the subsystem, we can design the block diagram. We're gonna add the output and the input of the block diagram. For the input, we're gonna use the step block, and for output, we're gonna use scope. This is the block diagram without the controller, which is open loop. So we're gonna put the input speed, which is 900 RPM first, and we're gonna see the output response. So this is the response, the graph response. So from this graph, we actually can find the parameters of the block of the transfer function by clicking the signal statistic and variable measurement. We can find the rise time, the peak value, the peak time from here. But as for this part, we're not gonna find it yet, so we're gonna skip it for now. Now, C determine PID gain manually. We already done that previously. And then D create the control system block diagram for manual tuning PID controller on MATLAB assembly. Okay. Now we're gonna design the block diagram of to simulate the PID gain that we get manually from using the clinical segment method. So this is the P controller, and the KP for P, the PKP gain is what we get from manual tuning. Now we're gonna run and see the response. This is the response, and we're gonna attach this on report for 900 and 150. Let's see for 1500. Response. Now I'm gonna design the PI controller for manual tuning gain. So this is the PI controller by using the gain from manual tuning. This is the KP gain, and this is the KI gain for PI controller. Now we can run the system. So this is the response for 1500 RPM, and then we change the input speed to 100 to see the response. Run. Here. So both response, we're gonna attach it on the report here. Next, I'm gonna design the PID controller using the manual tuning gain. So this is the PID controller by using the gain we get manually. Now we're gonna run. So this is the response for 900 RPM. We can see it have high overshoot, and then later it will stabilize. Now for 1500. So same like before. Okay, now we're done with the PID control block diagram for manual tuning. Next is create the system block diagram for automatic fine tuning PID controller on MATLAB assembly. So for automatic tuning, so this is the block diagram for automatic tuning. So to tune the PID parameters automatically, to find the KP, KI, KD automatically, we click tune here. So this is the automatic tuning graph response for. So to get the KP, KI, and KD, we click update block. And now we already have the value of KP, KI, and KD by automatic tuning. Now we can run the system and see the response. So the response is same like before. This is for 1500 RPM. You can see it has low overshoot, and then it will find stability here. We can see here. We can make the stop time higher and run it. You can see here. It will stabilize to 1500 later. This is the response for 900 RPM input speed. Okay, we're done with that automatic tuning. So it says here that we need to compare the response from automatic tuning and manual tuning of the PID controller. So to compare, we put the facility here and the scope here. Now, if we run the system, when we see at the scope, we can see the comparison of the response. So the yellow is the input speed, and then we have the subsystem tree, the blue. The blue one is the response of PID controller with manual gain. And for the purple one is response for PID controller with automatic gain. And then it say to check the maximum overshoot, rise time, settling time, peak time, and error condition stable. So we actually can find the parameters needed for this is the peak value, this is the peak time for the maximum overshoot. We can see it here, overshoots 9.341. This is for automatic. And then we have the rest time here 1.228. As for the manual gain, the peak time 1.564, rest time 185.784 milliseconds. The overshoot reach 80%. Okay, and then there is another method to find all the parameters needed. It is by clicking here. Then we're gonna put the manual gain value here. Reapply, and then we're gonna tune it. So we can see here is the comparison. For the dotted line is the block response of manual gain, and the tune response is the response for when we have the automatic tuning gain. And then we can see the parameter we needed here. For the manual, we can see the rise time, settling time, overshoot, the peak value, and closed loop stability, and as well as for the automatic tuning gain block diagram, block system. So it's a plot the comparison on the graph, on the report, sorry. So we have here, this is the response from automatic tuning before, the KPI and KD we get from automatic tuning, and then this is for the comparison, just like before here, the graph for automatic versus manual tuning, and then this is the comparison of the KPI and KD we get from manual and automatic, and then the response for 900 RPM and 1500 RPM, and then this is the parameter we get from automatic PID tuning, and this is the response, the parameter that we get from the graph response on the scope.
So as a conclusion, to conclude our research, the PID control system is vital to efficiently control the speed of a DC motor. And based on the results of simulation, the rise time will be reduced by proportional controller, but the steady state error will remain unresolved. On the other hand, an integral control will remove the steady state error, but the transient response will become much worse. And by boosting system stability, lowering overshoot, and effectively reducing overshoot using a derivative control, the transient response will improve positively. So PID stands for proportional integral derivative, and these three controllers are connected in a way that a control signal is generated. It will send control output at determined levels as a feedback controller. And PID controller instructions are also embedded into programmable logic controllers, and PID controllers are historically employed in process control applications due to their flexibility and dependability. The efficiency of controlling the blade speed with DC motor as an actuator is proven, and the advantages of using PID controller is that it helps to control the speed of DC motor very effectively. The reaction of PID controller is much greater than any other controllers. Thank you.
So lastly, thank you for spending your time with us.